Hello everyone. In this class, I will discuss a very important topic of differential calculus, which is partial differentiation. In this topic, uh, I will discuss a few examples related to partial differentiation. And first, I will discuss what is partial differentiation. So, as we have studied in 12th class, in which if we have function of one variable, we have y as a function of x, and where y is dependent variable and x is independent variable. And differentiation dy upon dx is the total differentiation, in which we have to differentiate y as a function of x, which represents the rate of change in y and with respect to the variable x, which is known as the change in independent variable with respect to the independent variable. As we know, suppose we have ds upon dt in physics, and which is the rate of change in displacement, which is known as the velocity. So this is rate of change in displacement with respect to time. So this represents the velocity. And similarly, we have dv upon dt, that is rate of change in velocity, which is known as the acceleration. So this is differentiation of one variable function, in which we have y as a function of x, where y is dependent variable and which depends on the x. And here we have s, which is displacement or distance, depends on displacement traveled in a certain time. So we have velocity, which is function of time. So ds upon dt is the rate of change in displacement, which is given by the velocity. And similarly, we have dv upon dt, which is rate of change in velocity, and this is acceleration actually. Now, here in this lecture, I will discuss the partial differentiation, or we will discuss here the differentiation of functions of more than one variables here. So, here in this discussion, suppose we have any function, like we have u as a function of x, y, z, and u is function of the variables x, y, and z, and we have to differentiate this u with respect to the variables x, y, and z. Then the partial differentiation of u with respect to x, suppose we have to differentiate first u as partial differentiation and with respect to x, then this is del u upon del x. Del u upon del x means this is differentiation with respect to x. It means the other variables like y and z will be treated as constant. So here, uh, if u is function of three independent variables x, y, and z, and we have to differentiate u as x, then we have to differentiate this function with respect to x and treating y and z as constant, and this is denoted by del u upon del x. And similarly, we have del u upon del y, the partial differentiation of u with respect to y and z. So this is treated as constant. So del u upon del y is partial differentiation with respect to y, in which we have y and z as constant. And similarly, we have del u upon del z, which is partial differentiation with respect to z, in which we have y, in which x and z as constant. Now this is the function f, which is function of x, y, z. So del f upon del x is the partial differentiation, which is also denoted by fx. So we have fx or del f upon del x, which is partial differentiation of f with respect to x, and treated y and z as constant here. And similarly, we have del f upon del y, in which we have partial differentiation of f with respect to y, and treated x and z as constant. And similarly, we have del f upon del z, in which we have partial differentiation of f with respect to z and treated x and y as constant. Now, we have the second and higher order derivative of the function. Suppose u is function of x, y, z, then del u upon del x, del u upon del y, and del u upon del z. These are the partial derivative of first order. And suppose we have to differentiate function further, suppose we have to find del u upon del 2 upon del x square, and this is the partial differentiation of function two times with respect to x. So first we have to find del u upon del x, it means partial differentiation of function with respect to x, then again differentiate the function with respect to x. So we get del 2 u upon del x square. And similarly, we have del 2 u upon del y square. So first we have to find del u upon del y, or partial differentiation of function with respect to y, then again we have to differentiate the function with respect to y partially. It means in both the derivatives, in this one y and z will be treated as constant, and similarly for this one x and z will be constant. In last one, if we are differentiating partially with respect to z, then x and z will be constant here. Now these are the partial derivatives of function with respect to x, y and z, and these are second order derivatives. And similarly, if we have to find out some other derivatives, like we have to find out del 2 upon del x del y. It means we have to differentiate the function with respect to y and z. So we can write del 2 upon del x square, del x del y, and this is also represented as del 2 u upon del y and del y del x. It means actually order is immaterial if these partial derivatives are continuous, or fx, fy and fz, these are continuous, then del 2 upon del x del y equals to del 2 upon del y del x, or both are same actually. Now we have some example here. If we have any function f which is x square plus xy plus y square, and we have to find x del f upon del x plus y del f upon del y, then first we have to differentiate the function with respect to x. So this is the function which is f, which is x square plus xy plus y square. Then first we have to find del f upon del x. It means partial differentiation of function with respect to x. Then we have the variable y as constant. So first we have to find del f upon del x. Del f upon del x means y will be constant here. So these are constant here. So first we have to differentiate this function, and differentiation of this one will be 2x. And y is constant here, so differentiation of x is 1 here. So del f upon del x is 2x plus y here. And similarly, we can find del f upon del y. Del f upon del y means this is partial differentiation of function with respect to y. So x will be constant here. So here if we differentiate this function with respect to y, then these terms will be constant here. So if we differentiate with respect to y, then this term will be 2y, which is 2y, and this is constant, and differentiation of y is actually 1. So we have del f upon del y, which is 2y plus x here. Now since we have to find x del f upon del x, so in del f upon del x multiplied with x, so we get del f x del f upon del x, which is 2x square plus yx. And similarly here we have to find y del f upon del y, which is 2x square plus yx. So now if we add these two functions, which is x del f upon del x and y del f upon del y, then we get 2x square plus yx plus 2x square plus xy. So finally we have x del f upon del x plus y del f upon del y, which is 2 times of this function, and this function is actually f. So we have x del f upon del x plus y del f upon del y equals to 2 times the given function. Now we have some more examples here, like first one is z equals to sine inverse x upon y. Then we have to find x del z upon del x plus y del z upon del y. Again we have same kind of function here. So let we have z is as sine inverse x upon y. Then first we have to find del z upon del x. So del z upon del x will be partial differentiation of function z with respect to x. It means if we are differentiating partially with respect to x, then y will be constant here. So if we differentiate this function with respect to x, then as we know differentiation of sine inverse x is actually, if we differentiate d upon dx of sine inverse x, then this is actually 1 upon root 1 minus x square. But here we have a function which is sine inverse x upon y. So this differentiation will be 1 upon 1 minus x upon y then whole square. So this is differentiation of sine inverse x upon y, but we have to differentiate this function also, which is x upon y. But if we are differentiating partially with respect to x, then y will be constant here. Y will be constant means we have 1 upon y, and differentiation of x is 1 here. So this is the del z upon del x here. So now again if we have to find del y upon del x, del z upon del y, then we have to differentiate again like this one, del z upon del x, which is del z upon del y, in which we have x as constant. So these are the values of del z upon del x and del z upon del y. So if we are differentiating this one, z with respect to y, then we have 1 upon 1 minus x upon y whole square. Then we have to differentiate x upon y with respect to y, which is minus x upon y square. So after simplification, we get the values of del z upon del x and del z upon del y. But here we have to find the function which is x del z upon del x plus y del z upon del y. It means first we have to multiply the function del z upon del x with x, which is x upon root y square minus x square, and del z upon del y will be x del y del z upon del y will be minus x upon root y square minus x square. So after adding these two, we get the value of x del z upon del x plus y del z upon del y, and which is equals to 0. So these are the differentiations of function z, which is actually sine inverse x upon y. So these are differentiations with respect to x and y. These are del z upon del x and del z upon del y. And after multiplying with x and y and after adding these, we get this value of this whole expression, which is x del z upon del x plus y del z upon del y. And similarly, we have some more examples here. Like we have u as function which is logarithm function of 10x plus 10y plus 10z, and we have to show some expression here which is sin 2x del u upon del x plus sin 2y del u upon del y plus sin 2z del u upon del z, and we have to show equals to 2. So first we have to find del u upon del x. Del u upon del x means partial differentiation of u with respect to x. So here y and z will be constant. So first we have to differentiate partially with respect to x. If we are differentiating this function with respect to x partially, and as we know, the differentiation of logarithm function is actually differentiation of log x is 1 upon x. So differentiation of this whole function will be 1 upon 10x plus 10y plus 10z. And then again differentiation of this function is sec square x. Since if we are differentiating this whole function, then y and z functions will be treated as constant here. So we get sec square x. Now here we have to find sin 2x del u upon del x. So if we multiplied this whole function with sin 2x means we have 2 sin x cos x. So here we have 2 sin x cos x, and this sec square x is actually 1 upon cos square x. So this cos square x will be here, 1 cos x will be cancelled here. So we get 2 sin x upon cos x. It means this is 2 tan x. So we have sin 2x del u upon del x as 2 tan x plus 2 tan x upon 10x plus 10y plus 10z. So we get the value of sin 2x del u upon del x. And similarly, we have sin 2y del u upon del y. So if we are having here del u upon del y, so in case of del u upon del y, this term will be sec square y. In case of del u upon del z, we have this term as sec square z. So we get sin 2y del u upon del y as 2 tan y upon 10x plus 10y plus 10z. And similarly, we have sin 2z del u upon del z, and which one equals to 2 tan z upon 10x plus 10y plus 10z. So these are the values of these functions: sin 2x del u upon del x, sin 2y del u upon del y, and sin 2z del u upon del z. Now after adding these, we get the value since denominator is same here, which is 10x plus 10y plus 10z, and similarly for all the functions in sin 2x del u upon del x, denominator is 10x plus 10y plus 10z, and for sin 2y del u upon del y is 10x plus 10y plus 10z, and for sin 2z del u upon del z is 10x plus 10y plus 10z. So after adding these, we get the denominator as 10x plus 10y plus 10z. In numerator, we have 2 10x plus 2 10y and 2 10z, and this will be cancelled out here. Finally, we get the value 2. So this is the value of sin 2x del u upon del x plus sin 2y del u upon del y and sin 2z del u upon del z, and which one equals to 2. Now we have one more example here, which is u equals to x square tan inverse y upon x minus y square tan inverse x upon y, and here we have to show the value of del 2u upon del x del y. It means we have to find del 2u upon del x del y. So first we have to find del u upon del y here. Let we have a function which is this one. Then del u upon del y will be the partial differentiation of u with respect to y. So first we have to differentiate u with respect to y. It means x will be constant here. So first we have to assume, or we have to treat x as constant. We get the differentiation of this one. So if x square is constant, then differentiation of tan inverse is this one. And for this one, since x is constant here, but y square is not constant. So we have differentiation of y square is 2y, and tan inverse will be as it is. And next term y square will be as it is, and differentiation of tan inverse x upon y is this one here. So this is the value of del u upon del y. But here we have to find del 2u upon del x del y. First we have to simplify this one. Since this term is actually, if we are taking LCM here, so x square plus y square in denominator, and this term will be x cube upon x square plus y square, and this term is actually x y square upon x square plus y square, and this term, middle term, is actually minus 2y tan inverse x upon y. So after simplification, since this term is actually, if we are taking x as common, so we have x square plus y square upon x square plus y square. So this term is actually x. The sum of these two terms will be x. So we have x minus 2y tan inverse x upon y. So this is the value of del u upon del y. But here we have to find del 2u upon del x del y. It means we have to differentiate this function with respect to x again. So in this operation, the variable y will be constant. Now we have to differentiate this one with respect to x. Then we get del 2u upon del x del y. So if we differentiate this one, this is actually del u upon del y. So we get this expression, which is x square minus y square upon x square plus y square. So this is the value of del 2u upon del x del y, which is x square minus y square upon x square plus y square for this function. Now we have one more example here, which is example of one more function, which is u equals to sine inverse x upon y and plus tan inverse y upon x. And we have to show x del u upon del x plus y del u upon del y equals to 0 here. So here first we have to find del u upon del x. So or differentiate the function u with respect to x partially. It means y will be constant here. Now del u upon del x is this one, which is given by this expression, and differentiation of sin inverse x is this one, and differentiation of tan inverse x is this one. Now we have to find the value of x del u upon del y, which is this one, x upon root y square minus x square minus xy upon x square plus y square. And similarly the value of del u upon del y, we have del z upon del y or del u upon del y, we have this one as u actually. This is del u upon del y, which is 1 upon root 1 minus x square upon y square into minus x upon y square, and plus we have 1 upon y square plus upon x square, 1 plus y square upon x square into 1 upon x. So this is the value of del u upon del y, and we have to find y del u upon del y here. So on adding these two, we get the value of x del u upon del x plus y del u upon del y, and which one is 0 actually. Now we have one more example, which is an example of function, and which is function of the form x plus ay, and another function which is of the form x minus ay. So if we have u as a function of x plus ay and plus another function which is of the form x minus ay, then we have to show del 2z upon del x square equals to a square del 2z upon del y square, or we have del 2u upon del x square equals to a square del 2u upon del y square. So first we have to assume the function which is of the form x plus ay and x minus ay. Then first we have to differentiate the function with respect to x partially. So if we are differentiating partially with respect to x, it means y will be constant here. So if we differentiate this function with respect to x, then first we get f dash x plus ay, and then again if we differentiate this function with respect to x, then this term will be 1 and rest will be 0. So we get del u upon del z or del z upon del x equals to f dash x plus ay, and similarly we have psi dash x minus ay. If we differentiate this function with respect to x, then we get 1 actually. Now if we again differentiate this function with respect to y, then we get f dash x plus ay, and if we differentiate this function, this term with respect to y, then we get a. So we get a f dash x plus ay. And similarly, if we differentiate this function, then we get minus a. So we have del z upon del y equals to a f dash x plus ay minus a psi dash x minus ay. And del 2z upon del x square will be, it means again differentiation of this function with respect to x. So again we get the f double dash x plus ay and psi double dash x minus ay. And if we differentiate this function with respect to y, then again we get a square f double dash x plus ay and plus a square psi double dash x minus ay. And we are seeing here is a square is common, so we get the value which is a square and del 2z upon del x square. So the value of del 2z upon del x square will be del x square actually. So this expression is actually del 2z upon del y square and equals to a square del 2z upon del x square. So this is the expression actually. So we can differentiate any function. If we have implicit function or some other kind, then we have some different kind of methods to find partial derivatives. Now we have one more example which is of a function which is u equals to e raised by x y z. Then we have to show del 3u upon del x, del y and del z, and which we have to show equals to 1 plus 3 x y z plus x square y square z square and e raised by x y z. So here we have to differentiate this function u with respect to x, y and z. So first we have to differentiate this one with respect to z. If we differentiate this function with respect to z, then we have exponential function. So differentiation of exponential will be as it is. But if we differentiate this one, which is x, y and z product, and with respect to x we are differentiating, so y and z will be constant here. So differentiation will be, if we are differentiating with respect to z, then x and y will be constant. So if we differentiate this function u equals to e raised by x, y, z, so del u upon del z will be e raised by x, y, z. And if we differentiate this x, y, z, then we get x, y. So we get the value of del u upon del z equals to x, y into e raised by x, y, z. And again, if we have to find del 2u upon del y del z, it means del 2u upon del y del z is del upon del z of del u upon del over del y of del u upon del z. So here we have to differentiate this function del u upon del z, means this function with respect to y. So if we differentiate this function, so this is actually function of y also, and this is also function of y. So we can differentiate this one by parts. So if we differentiate this function with respect to y, we get x, and second function will be as it is. And if we differentiate second function, so first will be as it is. So first will be as it is means x, y will be as it is. And if we differentiate e raised by x, y, z, and with respect to y we are differentiating, so we get xz, or we get x square yz. So we get the function which is x square yz plus x into e raised by x, y, z. So this is the partial differentiation of function with respect to y and z, which is del 2u upon del y del z. So del 2 upon del y del z is x square yz plus x into e raised by x, y, z. But we have to find del 3u upon del x, del y and del z. It means we have to differentiate one more time, and which is with respect to x here, because del 3u upon del x, del y, z is del over del x of del 2u upon del y del z. So we have to differentiate this function with respect to x. It means we have to differentiate by parts, or first we have to differentiate this function. So differentiation of this function is, differentiation of x is 1 here, and differentiation of this function is 2xy z, and second function as it is. And again now if we differentiate this function, since we have first function as it is, so we have to differentiate this function with respect to x. It means y and z will be constant here. So we get the differentiation of this function, which is equals to 1 plus 3xyz plus x square y square and z square into e raised by x, y, z. We can simplify this one. If we take common here, we have e raised by x, y, z as common. So first term is 1 here. We have 1 plus we have 2xyz, 2xy and z, and here we have yz inside the bracket. So we get x square y square z square. So we have plus x square y square and z square, and there is one more term which is x into yz. So we get this term as 3 times. So we have 1 plus 3xyz plus x square y square z square into e raised to x y z. So this is the value of partial differentiation in which we have del 3u upon del x, del y and del z. Now we have one more example which is related to partial differentiation, in which we have some implicit function of the form in which we have x is by x, y is by y and z is by z equals to c. Then we have to show at x equals to y equals to z, del 2z upon del x del y equals to x logarithm of ex whole power minus 1. So here we have x is by x, y is by y, z is by z equals to constant. So here we have to find del 2z upon del x del y del z. So first we have to take logarithm on both sides. On logarithm we get, as we know, logarithm of product of functions is equals to sum of logarithm of functions. Like we have, suppose this one, x is by x, y is by y and z is by z, and equals to logarithm of c. So we have logarithm of x is by x plus logarithm of y is by y and plus logarithm of z is by z and equals to logarithm of c. And as we know, if we have logarithm of x is by x, it means we can write this one as x logarithm of x, and again we have y logarithm of y and z logarithm of z and equals to logarithm of c. Now if we differentiate this one with respect to y, actually first we have to differentiate with respect to y, or we can differentiate this one as with respect to x also. We have similar kind of function here, symmetry here. So if we differentiate this one as with respect to x, then what we have here, if we differentiate this function with respect to x, is we are seeing there from here from this relation, since we have del 2z upon del x del y. So this shows that z is function of independent variables x and y. Z is function of x and y. It means x and y are independent variables here. It means if we differentiate x with respect to y, then we get 0. Since x and y are independent, independent means if we differentiate function with respect to x partially, then y will be treated as constant. Or if we differentiate function with respect to x partially, then y will be constant. If we differentiate with respect to y, then x will be constant. So here from this term, this shows that z is dependent variable and it depends on x and y. But so x and y are independent variables. So from here, if we differentiate this function with respect to x partially, this whole term, then first we have x as it is, and differentiation of log x is 1 upon x, and plus logarithm of x, and differentiation of x is 1 here. So this is the differentiation of first function, and second term will be 0 here, because x and y are independent and we are differentiating partially with respect to x. So this term will be 0. Now if we differentiate this one, so this whole term, so first function will be as it is here, and differentiation of log z is 1 upon z. So differentiation of log z is 1 upon z, then del z upon del x, which is outside the bracket here. And similarly, if we differentiate this function z, which is 1 here, and log z, and then we have del z upon del x outside the bracket and equals to constant. So we have this one as 0. Or from here we have 1 plus log x. So this term is actually 1 plus log x. So we have 1 plus logarithm of x and plus 1 plus logarithm of z, and we have del z upon del x and equals to 0. So value of del z upon del x is minus 1 plus logarithm of x upon 1 plus logarithm of z here. And similarly, we have del z upon del y equals to minus 1 plus logarithm of y upon 1 plus logarithm of z. In this del z upon del y, this term, first term will be 0. So we get the value of del z upon del y, which is minus 1 plus logarithm of y upon 1 plus logarithm of z. But here we have to find del 2z upon del x del y. It means either we have to differentiate this function with respect to x, or we have to differentiate this function with respect to y. So if we differentiate this one with respect to x, then we get del 2z upon del x del y. So we get del 2z upon del x del y equals to del over del x of del z upon del y. So we have del over del x of this term, this function which is del z upon del y. It means we have to differentiate this minus 1 plus logarithm of y upon 1 plus logarithm of z. So if we differentiate this function with respect to x, it means z will be treated as constant. So z will be y will be constant and z will be function of x here. So if we differentiate this function, so we get the value, since this term is constant here, so we get minus 1 plus logarithm of y. Then we have del over del x of this 1 upon 1 plus log z. So after differentiating this function, we get minus 1 plus log z whole power minus 2, and then differentiation of this one which is 1 upon z, and differentiation of z with respect to x will be del z upon del x, and which is minus 1 plus log x upon 1 plus log z, which is given here. So this is the value of del 2z upon del x del y. Now since we have to show some value of del 2z upon del x del y at x equals to y equals to z. So if we put, since the expression which we have to show is in terms of x, so if we put y equals to x and z equals to x, or we have to put y and z in terms of x, then we get the expression this one, which is minus 1 upon x 1 plus logarithm of x. And since we know that this 1 is actually, since we have minus 1 upon x, and this 1 can be written as logarithm of e and plus logarithm of x, so which is minus 1 upon x, and this is logarithm of ex. So we get minus 1 upon x logarithm of ex. So this is the required expression which we have to show, which is x logarithm of ex and whole power minus 1. And that's all from this class. Thank you.